In the late 1990s and early 2000s, many vehicles developed reputations for lasting well past 200,000 miles when properly maintained. Mechanics expected it. The owners planned for it. Engines were designed with wide safety margins, and the average car contained far fewer electronic systems than the vehicles we drive today. 2 decades later, the automotive industry looks very different. According to data from the National Highway Traffic Safety Administration, the number of vehicle recalls issued in recent years has climbed dramatically compared with the early 2000s. In 2023 alone, the National Highway Traffic Safety Administration reported around 1,000 recall campaigns affecting roughly 39 million vehicles and equipment items in the United States. Many of these recalls are tied not to traditional mechanical problems, but to electronic systems, sensors, and software. This shift surprises many drivers. Modern cars are built in factories filled with robotics and precision equipment. Engineers have access to computer modeling tools that did not exist 20 years ago. Material science has improved. Manufacturing tolerances are tighter than ever. In theory, vehicles should be more reliable. But reliability statistics and repair data tell a different story. Recent vehicle dependability studies have reported increasing numbers of owner-reported problems in areas such as infotainment systems, connectivity features, and other software-driven components. The reason is not poor engineering talent or careless manufacturing. Changes in regulations, engineering priorities, and manufacturing strategy have reshaped the balance between efficiency, cost, and long-term mechanical simplicity. Over the past 2 decades, car manufacturers gradually redesigned vehicles around 3 priorities: regulatory compliance, manufacturing efficiency, and profit margin. Long-term durability is now balanced against other priorities such as emissions compliance, fuel economy, advanced technology, and manufacturing cost. If you walk through a dealership lot today, you see dozens of brands competing for your attention. Trucks, sedans, SUVs, crossovers, each promising more power, more technology, and more features than the model that came before it. But under the surface, the industry is not as diverse as it appears. Many vehicles share the same engineering architecture. Many engines rely on the same modern technologies. And many of the systems that improved efficiency also introduced new long-term reliability risks. To understand how reliability changed so dramatically, you have to look at the engineering decisions that reshaped the modern automobile. The reliability plateau of the early 2000s. During the late 1990s and early 2000s, many manufacturers reached what engineers sometimes describe as a durability plateau. Engines developed during that era had already benefited from decades of mechanical refinement. Manufacturing techniques were mature. Most common design flaws had been corrected through years of production experience. Engines such as Toyota's long-running 4-cylinder families, Honda's K-Series engines, and General Motors' LS-based V8 platforms became known for their ability to run hundreds of thousands of miles with routine maintenance. These engines shared several characteristics. They were naturally aspirated. They used port fuel injection. Internal pressures and temperatures remained moderate. The number of moving components inside the engine was relatively small. They were not the most fuel-efficient engines by modern standards, but they were simple, durable, and predictable to maintain. That design philosophy began to change during the late 2000s. The Regulation Tradeoff. One of the biggest forces shaping modern vehicles is fuel economy regulation. Governments around the world introduced stricter efficiency standards in response to environmental concerns and rising fuel costs. In the United States, corporate average fuel economy requirements steadily increased after the financial crisis of 2008. Manufacturers needed to reduce fuel consumption across their fleets. One of the most effective ways to accomplish this was a process known as engine downsizing. Instead of building larger naturally aspirated engines, companies began installing smaller engines equipped with turbochargers. A turbocharger allows a smaller engine to produce the same power as a larger one by forcing additional air into the combustion chamber. This approach works extremely well in fuel economy testing. Under light driving conditions, the smaller engine burns less fuel, During acceleration, the turbocharger increases power output so the vehicle still feels strong. But the engineering trade-off is significant. Turbocharged engines operate at higher internal pressures and higher temperatures. The components inside the engine must endure more stress than those inside older, naturally aspirated designs. That stress can accelerate wear over time. Direct injection and carbon buildup. Another technology introduced to improve fuel efficiency is direct fuel injection. In a traditional port-injected engine, fuel is sprayed into the intake port before entering the combustion chamber. As the fuel flows past the intake valves, it helps wash away carbon deposits created during combustion. Direct injection engines work differently. Fuel is sprayed directly into the combustion chamber at extremely high pressure. This improves fuel atomization and allows the engine to run more efficiently. But it removes the cleaning effect that port injection provided. Over time, carbon deposits can accumulate on the intake valves. These deposits restrict airflow and can lead to rough running, hesitation, and reduced engine performance. Many mechanics now perform a service known as walnut blasting to remove those deposits. The process uses crushed walnut shells blasted through the intake ports to clean the valves. The service can cost several $100s depending on the engine. It is considered maintenance, not a defect, and typically falls outside warranty coverage. The Turbocharger Equation. Turbochargers themselves introduce another reliability variable. A turbocharger is powered by exhaust gases that spin a turbine connected to a compressor. This compressor forces more air into the engine, increasing power output. While this system improves efficiency and performance, turbochargers operate under extreme heat. After the engine shuts down, heat from the turbocharger can cause oil trapped inside the system to break down and form carbon deposits. Over time, those deposits can damage the bearings that support the turbocharger shaft. When the bearings wear out, the turbocharger must be replaced. Replacement costs can range from $1,500 to several $1,000s depending on the vehicle. When turbochargers fail later in a vehicle's life, replacement can be expensive. The transmission revolution. Engine design is not the only area where complexity increased. Automatic transmissions have also changed dramatically. 20 years ago, most vehicles used 4-speed or 5-speed automatic transmissions. These gearboxes were relatively simple, with fewer internal components and straightforward hydraulic control systems. Today, it is common to see transmissions with 8, 9, or even 10 forward gears. These additional gears allow the engine to operate at lower speeds during highway driving, improving fuel efficiency. But each additional gear requires more clutch packs, more control valves, and more sophisticated software. Modern transmissions rely heavily on electronic control modules that manage shift timing, clutch engagement, and torque converter behavior. When these systems malfunction, repairs can be extremely expensive. In some cases, manufacturers recommend replacing the transmission assembly rather than rebuilding it, which can increase repair costs. Platform sharing and global manufacturing. At the same time that engines and transmissions became more complex, manufacturers began reorganizing the way vehicles were developed. To reduce development costs, many companies adopted a system known as platform sharing. A single platform can serve as the foundation for dozens of vehicles across multiple brands. For example, one chassis architecture might support a compact sedan, a crossover SUV, and a luxury model sold under a different brand name. This strategy reduces engineering expenses and allows manufacturers to build large numbers of vehicles using shared components. The downside is that a design flaw in one component can affect millions of vehicles. When a shared transmission design or electronic module develops a problem, every model built on that platform may experience the same issue. Material substitution. Cost reduction efforts also changed the materials used in many modern vehicles. In earlier decades, many engine and cooling system components were constructed from metal. Today it is common to find plastic intake manifolds, plastic thermostat housings, and plastic cooling system connectors. Plastic is lighter and cheaper to manufacture. It also helps reduce vehicle weight, which improves fuel economy. But plastic components exposed to constant heat cycles can become brittle over time. On some vehicles, plastic cooling components can become brittle after years of heat cycling and may eventually require replacement. These components may be inexpensive to manufacture, but replacement can still require hours of labor. The emissions system layer. Modern engines must also meet strict emission standards. To achieve those standards, manufacturers install a variety of additional systems designed to control pollutants. These systems may include exhaust gas recirculation valves, catalytic converters equipped with oxygen sensors, diesel particulate filters, and selective catalytic reduction systems. Each of these components adds complexity to the vehicle. If one sensor fails or one valve stops operating correctly, the engine management system may trigger a warning light or reduce engine power. The engine itself may still function properly, but the emission system can prevent the vehicle from operating normally until the issue is repaired. The rise of automotive software. Perhaps the biggest change in modern vehicles is the role of software. Vehicles built 20 years ago typically contained far fewer electronic control units than modern cars. Modern vehicles may contain more than 70. Some modern vehicles can contain 70 to more than 100 electronic control units, depending on the model and equipment level. These modules communicate through high-speed data networks that coordinate everything from braking systems to driver assistance features. If one module loses communication with the network, the vehicle may disable certain functions or enter a reduced power mode. Diagnosing these issues often requires specialized diagnostic software available primarily at authorized dealerships. Independent repair shops can sometimes perform these repairs, but access to proprietary software and calibration tools is increasingly restricted. The warranty window. Despite the complexity of modern vehicles, most manufacturers still offer warranties that last only a few years. 3 years or 36,000 miles for bumper-to-bumper coverage. 5 years or 60,000 miles for the powertrain. These warranties provide reassurance to buyers purchasing a new vehicle. These warranties create a clear coverage window that defines how long manufacturers guarantee the vehicle's performance. Components that survive the warranty period have technically fulfilled their obligation. Repairs required beyond that window fall to the owner. What reliable vehicles still have in common? While the automotive landscape has changed, certain engineering characteristics still tend to support long-term reliability. Vehicles with naturally aspirated engines generally experience lower internal stress than heavily turbocharged engines. Engines that have remained in production for many years often benefit from extensive real-world testing and gradual refinement. Simple designs with fewer electronic dependencies can be easier and less expensive to maintain over time. Real Tradeoff. Modern vehicles deliver impressive capabilities. They are safer, more efficient, and more technologically advanced than the cars built 2 decades ago. Driver assistance systems help prevent accidents. Fuel efficiency reduces operating costs. Connectivity features integrate vehicles with smartphones and navigation systems. But every improvement introduces additional complexity. And complexity changes the reliability equation. The modern automobile is not necessarily less advanced. It is simply optimized for different priorities. Fuel economy regulations, emissions compliance, manufacturing efficiency, and competitive pricing all shape the engineering decisions behind today's vehicles. Durability beyond the warranty period is no longer the sole measure of success. When you look past the marketing and the technology features, one principle still holds true. Brand names sell vehicles, but long-term reliability comes from the engineering design hidden beneath the body panels.